Hello everyone, this is Mr. 2x, math teacher in Belgium. In this video, we'll talk about the first property of inverses. So, in the previous video, we learned about the purpose of inverse function. So I remind you, the purpose is to find for a specific function, a specific operation, the one that cancels this operation. So, to understand that pretty important property, we'll use a little activity. So I give you here a list of operations, and for each one I want you to find the operation that cancels the one in the list. Some are pretty obvious, some others you have to think about a little bit. So if you want to try it, so put this video on pause and then we check it out. So for the first one, what cancels adding 1 to a real number? It seems pretty easy and obvious that we only need to subtract 1. So I use a little scheme to present this instead of plain English. And you will see, theoretically, it will remind you of something that you learned at college. So we'll take a real number x, we add 1, it gives us, of course, x plus 1, and then if we subtract 1 to that result, it gives us x plus 1 minus 1. And it gives us, of course, x. What about cancelling subtracting 1 to a real number? Of course, we only need to add 1 to that result. If we use our little scheme, we take x, we subtract 1 to the results, it gives us x minus 1. And if we add 1 to that result, it gives us, of course, x minus 1 plus 1, that gives us x. We get back at the start. It seems okay, pretty obvious. Let's try something more complicated. So, let's multiply a real number by 2. What cancels that operation? Of course, we need to divide by 2. So if we take x, we multiply it by 2, it gives us 2x. After that, if we divide 2x by 2, it gives us, of course, x. So, and what about dividing by 2? What cancels that? It seems also obvious and trivial that we only need to multiply by 2. So let's take x, we divide it by 2, it gives us x over 2, and if we multiply by 2 this result, it gives us, of course, x. So here it was for the four element operations there, they were pretty easy because there was only one operation at stake. So what happens if more operations, sub-operations are present in one operation? As first multiplying by 3 and then subtracted by 1. What cancels that operation? It's not so simple as the previous ones. What we can do is to use our little scheme to represent this operation and then use our little scheme eventually backwards. Let's see what it gives us. So we have x. We want first to multiply by 3, so it gives us 3x, and then we subtract by 1, it gives us 3x minus 1. So what can we do to construct our inverse? Inverse, you can think of that as backwards, to get back at the start. So instead to go left to the right, what we can do is go right to the left. Let's see if that works. So we start with a real number. We verify if it works after. We take x, we go backwards, so what cancels minus 1? Of course, adding 1. We learned that in the previous slide. So after that, what cancels multiplying by 3? Of course, divided by 3. So it seems we have to check that in some way, that what cancels 3x minus 1 is 1/3 of x plus 1. What about first dividing by 2 and then adding to that result? Let's try something like 5. So we take a real number x, we divide it by 2, it gives us x over 2, and adding 2, it gives us x over 2 plus 2. So let's go backwards. Let's see what it gives us. So what cancels plus 2? Of course, minus 2. What cancels dividing by 2? Of course, multiplying by 2. So it seems also we have that verify also that the operations that cancel x over 2 plus 2 is 2 times x minus 2. So let's see what happens now in terms of functions. Here we saw this only in terms of or as arithmetic operations. What happens if we think of this as in terms of functions? So for 1 and 2, because they were the same, we had that little scheme. So the first one and the second one. So what are the two operations that we are working with? Adding 1 and subtracting 1. So if we think of that as functions, we can think of that as a function x plus 1 and a function x minus 1. You can see this here. So does this little scheme here remind you of something? I'm pretty sure you all have already seen this somewhere. What are we doing here? We are doing more than one operation after each other. One operation after another one, etc., etc. Does that remind you of something? Of course, it's composition of functions. What you are doing here is composing two functions with each other. Here you are composing x minus 1 with x plus 1. In here backwards. So here what you can see is that f after g, so it's, let's see, it's here, it's the second one, f after g, and gives us x. And also g after f gives us x. It's here. So it's a pretty neat property, isn't it? So we see here that if we compose those two functions, the two operations that we wanted to study, it gives us always x when we compose those functions. And for each type of a composition, the 2 has to give us x when we compose them. Let's see what happens for 3 and 4. We had those little scheme. What were the two functions that we studied, analyzed? 2x and x over 2. And so, when we are analyzing f after g, it's here, it gives us also x. And g after f, it's Here, g after f, fg, it gives us also x. So it seems that we have a pretty nice property here. So is that when we compose the two functions, whatever order we are composing, it gives us always x. And it has to gives us x to have co-inverses. Let's check it out. Let's check it for 5 and 6. Sorry. So for 5, we had those schemes. So what were the two functions? Here the two functions were 3x minus 1 and 1/3 of x plus 1. Does it help that when we compose them in whatever order that it gives us x? Let's see. F after g. So f after g, we take the function f, this one, and replace x by 1/3 of x plus 1. So it gives us what we have here on the screen. Here we see that the 3 and the 3 cancels each other. So we have x plus 1 minus 1, it gives us x. That's okay. It works. And what about g after f? G after f, so we take the expression of g, it's this one, and replace x by 3x minus 1. So we see here that the minus 1 and the plus 1 cancels, and after that the 3 and here the 3, the 1/3 and the 3 cancels also, and it gives us also x. So it seems to work, that property. What about 6? We had those schemes. So the two operations, the two functions that we are analyzing, it's x over 2 plus 2 and 2 times x minus 2. So what about f after g? So we take the expression of f and replace the x by the expression of g. Like here on the screen. We see here that the 2 cancels, and then the minus 2 and the plus 2 here cancels also, and it gives us x. So it works. It's okay. And what about g after f? So we take g and replace x by x over 2 plus 2. So here we distribute the 2 over each term. Here it gives us x, and then here it gives us plus 4. And then we have x plus 4 minus 4, it gives us x. So it seems that property seems to work. So, and that property is a very, very important analytical property of inverses. This property has always to be true. It has always to be verified if you want to know if two functions are inverses of each other. So if you have two functions, f and g, and if you want to be, if they have to be inverses of each other, you have to verify that f after g and g after f always gives us x. If it gives us something else than x, then they are not inverses of each other. It's a very, very important property of inverses, of inverse functions. So let's try it on some examples. So if we take those two functions, they are pretty complicated, isn't it? So we'll check this property. Let's calculate f after g and g after f. So f after g, we take f, the expression of f, and replace the x by x at the fourth plus 1. So here the plus 1 and the minus 1 cancels. We have this, and of course, the fourth root and the x to the fourth cancels, and it gives us x. So it's okay. G after f, we take the expression of g and replace the x by the expression of f. So here the fourth root and the fourth here cancels. It gives us x minus 1 plus 1, and it gives us x. So it's okay. So the two functions are inverses of each other. Quite. You understand that later. What about those two functions? Pretty complicated also. So let's check it out. F after g, we take the expression of f and replace dx by the expression of g. So it gives us this, minus 1 and plus 1 cancels. We have to compute the inverse of the inverse of x, and of course it gives us x. It's okay. The property is verified. And what about g after f? We take the expression of g and replace dx by 1 over x plus 1. So this gives us x plus 1 minus 1 gives us x. So also it's okay. So the property is verified. So the two functions must be inverses of each other. And what about those two functions? Let's compute f after g. So f after g, we take the expression of f, replace the x by square root of x plus 1. The square root and square cancels. It gives us x plus 1, so it gives us x plus 2. So here it's different from x, and here we can already say that those two functions are not inverses of each other, because the result does not give us x for this third composition. So I hope that you enjoyed this video and that you learned this very important property of inverses. So this property is always to be verified if you want to check algebraically if two functions are inverses of each other. So thumbs up if you think that this video can help somebody else to understand inverses. Transfer this video to him. And otherwise, I'll say you goodbye. Bye bye.